What's up, everyone? Today we're going to do an interesting problem called the 0-1 knapsack problem. So, as you can see here, we have a sort of long description of what it is. And the idea here is that we can imagine that we have a knapsack that's capable of carrying a certain amount of weight. And we have a set of items that we want to put into that knapsack. So our goal is to select, and let's say that those items have a dollar value. So one item is $10, one item is $20, etc. What we want to do is select the maximum number of items, or the items that actually have the greatest total sum value, that are within the weight that the knapsack can hold, to put into the knapsack. Because the idea would be like you're going to the store and you want to take the most valuable items that you can to then sell for money. And so you can see that we've sort of codified the problem a little bit into more specific terminology here. So we have a list of weights and a list of values, and then we have a maximum weight. And our goal is to find the maximum value. So the way that we have this formatted here, the weights match up with the values. So weight 0 and value 0 are like the same item. So it's the weight and the value for a given item. And so in this case, you can see that we have 3 different items to choose from. And then in this case, the maximum weight is 50. And so the maximum value you can create is 220. Because if you select the second and third items, that's 220 units of value, and it weighs exactly 50 units. So that would be light enough that we could fit all that into the knapsack, but it gives us the maximum value. And so our goal with this problem is to, given an arbitrary list of weights and values and max weight, we want to find what the maximum value is that we can choose. So let's talk about this problem a little bit. The first thing we probably want to do is just clarify what our input is formatted as. Because there are a lot of ways that you could do this. For example, you could have an item object that would include a weight and a value, and you could just take in an array of item objects. You could have what we have here, which is that you have just a list of weights and a list of values, and the indices match up. You could potentially do something else entirely. So in this case, I'm going to do it based on just having these 2 separate arrays that I'm going to take as input. But you could totally structure this as a list of objects. And that might be a decent way to do it, especially if your interviewer is happy with that. So you should definitely ask them what they would prefer. And let's talk about how we're actually going to solve this problem. So one way that we could think about this is by starting with the first item. And for each item, you either want to include the item in your backpack, or you want to discard the item or ignore the item. And so we could define a recursive function that would basically go through and find every possible combination of different items that we could choose from that are going to stay under our max weight. And then we could just return the maximum value of all of those. And so what we're basically saying here is that we're going to write a recursive function that is going to say, well, it's going to take in an index. So we're going to start with the first one, and then we're going to recursively, so we'll start with the first item, and we'll consider 2 cases. We'll consider the case where we include the item and the case where we exclude the item. And so we will call our function recursively 2 times, one where we included the item and one where we excluded the item, and then compare the results. And so we can just simply take the max value of including it and not including it. And as we continue and we iterate through each element, then eventually we're going to bubble up back the maximum response. So this is a fairly, I think, intuitive way to do this relative to maybe other ways that we could think about it. So I want to start with this because this will give us a foundation to jump off of, and the code is not very complicated. So let's go ahead and we'll code up this recursive version of this problem. So I'm going to call this public. It's going to return an integer, and I'm going to call it knapsack. And it's going to take in a couple things. It's going to take in an int w, which is going to be the max weight. It's going to take in the array of weights, and it's going to take in the array of values. So now what we probably want to do is just verify that our input is valid. So I'm actually not going to do that in the code here, but you can ask your interviewer or just mention to them that you would validate it. So for example, we need to know that weights and vowels have the same length, right? Because they're two different representations of the same set of objects. And so if they're not the same length, then that doesn't really make any sense, and we could have a index out of bounds exception. And we might also want to make sure, for example, that all of the weights are positive or all of the values are positive, although that's not necessarily a restriction that we would have on this problem. So that's something you may want to clarify with your interviewer as well, whether or not those sorts of cases are things that you're going to have to deal with. In this case, I'm just going to assume that the input is valid and that everything is like a 0 or positive integer. So we're going to then, we are iterating through our list, right? So we're going to need an index to keep track of which element we're looking at in our list. And so to do that, I'm going to overload this function with another knapsack that's also going to take in it's going to have the same signature, but it's also going to take in an index. And so that way we can, as we recursively call it, we can say what index to look at. And so this is going to take an int w, int weights, int vowels, and it's also going to take in an int I, which is just going to be our index. So now we have these two functions, and in the case of our first function, all we need to do is call our private function once with the 0 index, because we're just going to start things running. And so this is just going to be knapsack w weights vowels and 0. And now let's look at the interesting part, which is this overloaded function. So the first thing that we want to do is figure out what our base case is. So our base case in this case is going to be, let's see. So if the length of I, or if I is equal to the length of our array, or the number of elements. So we got to the last element, or we actually got past the last element, because I minus 1 is going to be the last item in our list, right? So it doesn't matter if we use the length of weights or vowels, because they should have the same value, but we're going to just say if I equals, in this case, weights.length, I'm just going to return 0. And the reason I'm going to return 0 in this case is that I know that that in this case I'm not going to add any additional value because I'm out of elements to add. So the value of 0 items is going to just be 0. And then once I check my base case, I'm going to have to check another case. So if my item that I have is greater than the amount of weight that I have available, greater than the max weight, if the weight of the element is greater than the max weight, then there's no possible way that I can include that in my knapsack, right? Because if there was, then I would immediately go over my max weight just by including this one item. And so I'm going to add a case for that, because we know that we always are going to skip the item if it's too big, basically. And so I'm going to say if w minus weights I, so w minus weights I in this case is going to be the weight left over after I add that element. If w minus weights I is less than 0, so if it's 0, it's fine, but if it's less than 0, I'm just going to return knapsack w weights vowels and I plus 1. So I'm just incrementing my I without changing anything else. Then otherwise, if my, and I'm going to break this down to a new line so it's slightly easier to see. Otherwise, what I want to do is try both possibilities, right? I want to try the version where I include this weight, and I want to try the version where I include this item, and I want to try the version where I exclude this item. And so to do that, I just have to find the max of the two values. So I'm going to return math.max of knapsack weight w minus weights I, because I am including that, and so the remaining weight that I have available for items to put in is now the total weight that I had before minus the weight of that element. Weights I, then weights vals I plus 1, and then I need to add the value of my current element, right? Because I am saying that I am trying to compute the actual value here. I'm not worrying about the specific elements. I just want the value. And so if I'm including that item in my knapsack, then that item's value gets included. So val plus vals I. So that's my first possibility. And then my second possibility is going to be knapsack w weights. It's the same as what we have before. Vals I plus 1. So the first case we had was, here is when we include the current weight. And then the second one is, the current item. And then this one is when we exclude the current item. So one of those has to be the ultimate result. And so I'm just going to find the max of those and return that. So that's all there is to this particular iteration of the solution. The only thing left is obviously to test it and then to figure out what the time complexity is. So I'm not actually going to go through and test it myself. I'm going to let you guys do that because I want to have time to move on to more interesting solutions. But just very briefly to look at the time complexity, the way that I think about this problem is that I actually think about it in terms of what I'm doing on a conceptual level rather than the code itself. And I think that can be really helpful sometimes, especially when the code gets kind of confusing, because I'm not exactly sure how I'd break down this code. But what I can do is I know that my algorithm takes a set of values and then looks at every possible combination of either including or excluding each value. So another way to look at it would be you have a list of items, and each of those items has either a Boolean value of true or false, which is just going to be whether or not the value is included. And so we can pretty easily get from this that the maximum number of possibilities we have is going to be, if you convert this into binary, it's going to be 7, or 7 plus the case where we don't include any. So the maximum here with 3 items is going to be 8. And then it's pretty easy to expand from this. Since it's binary, we just know that it's going to be O of 2 to the n. And so that's how we get the time complexity here. It's not really rocket science. It's just thinking about it logically through how we're solving the problem. And so what I want to move on to now is ways that we can improve upon this solution. So the first thing that's hopefully in the back of your mind, just because we're doing recursion here, is that maybe we could do some sort of dynamic programming. So dynamic programming relies on 2 things. You have to have optimal substructure, and you have to have overlapping subproblems. So optimal substructure, we already know we have because it's recursive. And that basically means that by solving the subproblems, you can solve the greater problem. Or by knowing the solution to the subproblem, you can then get the solution to the overall problem. So we know that because we're doing that because of the recursion. And then in terms of overlapping subproblems, that just means that we're calling our function multiple times with the same inputs. And in this case, the only inputs that can change are W and I. So the only thing that is actually going to vary are those 2. And so what we could do here is just modify our solution that we have right now by adding a cache. We could just save the values as we compute them. So when you return a value, you save it into the cache, and then future times when you want to compute the same value, you look in the cache first and then return the value if it's in the cache, and if not, then you would go and actually compute it. So that would be one way that we could do this, and I highly recommend that you try that on your own time. But another thing that we could do is build a bottom-up solution. And so what we have right here is a top-down solution, which basically means we're starting with the end result in mind and we're breaking it into smaller subproblems. But a bottom-up solution means that you start with the subproblems and build up to your final result. And so let's think about how we could do that. What we're basically going to want to do is look at all the possible values of I and W that are from 0 up to the final result. And what we're going to do, and we have to define what exactly this is going to mean. So I'm going to start by creating a 2D array, and it's going to be a 5 by 4 array. And what this is going to represent, and also I'm going to divide all of these values by 10 because it's going to make this array much more manageable. So this array is going to be in the vertical is going to represent I. So we're going to have I is equal to 0, 1, 2, and 3. And then the columns are going to be W, which are going to be 0, 1, 2, 3, 4, and actually we need one more because it should go up to 5. It should go up to our max weight. And so we also want to define what the values in our cells actually represent. And so what I'm going to say is that the values in this cell are going to be the maximum value of the maximum possible value for that max weight, given that the items included only includes the first I items. So for example, in this row, all of the values are going to be 0 because we're including 0 items. And then in this row, the values can at most be 6 because we can only include the first item. Even whatever the maximum weight is, the value can only be 6. And then this row can include the first 2 items, and then the last row can include all the items. And then the same is true for the weight. So in the first column, it's going to be 0 because for 0 weight, you can only include an item if you have a 0 weight item, but we're assuming that we don't. And so what we're going to do is then go through this iteratively and see how we can compute values further down in our table from the initial values that we have. So when we initialize, and then finally, we're going to get what's the max weight for, or what's the max value for all of the items with the max weight of 5, which is the problem that we're trying to solve. And then finally, once we compute it all, we can just return this value. So in terms of actually going about solving this, we know for starters, as I mentioned, that this row and this column are going to all be initialized to 0. So they're not going to change. And then we're going to want to fill in the rest of this table. So we can start with, let's go through one row at a time. We see that in this case, the max weight is 1. So we can include our first item, which has a value of 6. And then that's going to be true for this whole thing because because the weights increase, but we can only include the first item. Then in this second row, we know that we can say that we can include the first 2 items. And so now it gets a little bit more interesting because we're going to say that either we include the item or we don't include the item, right? So it's going to be exactly the same as what we were doing with the recursive solution. And first we have to check, obviously, if by including the item, we're going to go over our weight limit or not. So in this case, we know that we're going to go over our weight limit, and so we have to exclude the item. But what is the max value of all the items up until that item, not including that item? It's just this previous cell that we already computed, because this is just the same value but only including the first item. And now if we don't include the second item, it's just the same value. And so we just look here. Now when we get to here, we can see that we can actually include our second item. And so we need to make a choice. We need to decide whether the value is greater if we include the second item or not. And so our maximum weight is 2. And we can look at our two possibilities. So one is this, which is what we looked at before, and it's if we don't include the item. And then two is going to be if we included the item, we get the value of that item, but then we have to subtract the weight of that item. So we can look here at whatever the maximum is if we included that item minus the weight. And so we get that we have the max of either 6 or 0 plus 10, which in this case is 10. And so, of course, this throws off my whole table, but we can now go to the next one and do the same thing again. We have our max weight is 3, so we get the maximum of 6 or 10 plus this minus 2, which is 6, so 16. And so we have a new maximum. And we can continue this way. We're going to get, in this case, it's going to be 16 again because it's going to be 16 again because we have 10. And what I forgot to mention actually before is we need to look in this previous row because we don't want to include the 2 a second time, or the second element a second time. And so we have to look in this previous row, and we get again 6 plus 10 is going to be 16, and then we're going to have the same thing, 6 plus 10 is going to be 16. And I'll just space these out a little more. So now that we calculated that third row, we can move on to the last row. And again, we get 0 in the first column. Our max weight is 1. We can still 3, our weight here is 3, so it's not going to be valid. And so we can't include that. Again, the second one, we can't include it, 10. But now we can look at whether 16 or this 12 plus 3 minus 3, which is 0, is going to be greater. And so in this case, it's 16. And then we do it again. So we get 12 plus 6, which is going to be 18 now. And then our final one, we get 12 plus 10 is going to be 22. And if you remember, our old value was 220, and so we divide everything by 10. So what we get here is that we're just building it up by looking at those subproblems. And so in terms of space and time complexity, this is going to take a space and time complexity that's going to be proportional to the number of items and also to the max weight, because we have those two dimensions. So it's going to be so our time complexity is going to be O of n, which can be the number of items, times W. And so hopefully that makes sense. We can go ahead and code this up. It's actually going to be pretty easy for us to code now that we understand how this works. So we're just going to do public int again, and then knapsack. And it's going to take in, again, the same values. It's going to take in a W, it's going to take in the weights, and it's going to take in vowels. And now, again, we can check our parameters and make sure that that our input is valid. But I'm going to go ahead and assume that the input is valid. So we're just going to create a new cache. So int, it's going to be a 2D array. Cache is going to be a new int. And then we actually, as you probably noticed here, we are going to have to make our array is going to be weights plus 1, or items length plus 1 and max weight plus 1, because we want to start with the 0 and 0 and then go up to and including our final result. So we need to do, it's going to be weights.length plus 1 and W plus 1. And now let's fill in our array. So we're going to say for int I equals 1, because we don't need to look at the first row because we know that it's going to be 0. For I equals 1, I is less than or equal to weights.length. So going through the whole thing. And I plus plus. Then we're going to do another loop. Obviously, we're going to do for int j equals 0. J is less than or equal to W, and J++. And now all we need is our two possibilities. So remember what the two options were. It was either that our item is too big for the current max weight, and so we can't include it at all, or we want to decide whether to include it or not. So let's start with if it's too big. So if it's too big, that would basically mean that if weights I minus 1, and we're going to do minus 1 because it's a little confusing, unfortunately, the way that we're using this, but basically we want the one index to be the first item and the second index to be the second item, and same here. And so we need to refer to them as weights I minus 1, unfortunately, but hopefully it makes sense. And then if that's greater than j, because remember j is our current maximum weight that we're looking at for this subproblem. If that's the case, then we're going to say cache ij equals cache I minus 1j. And that's all. We just have to set the cache value to be the previous cache value, or the cache value for the previous same value of w, as we talked about here. Then otherwise, if we do want to actually consider both possibilities, we're going to say else cache is going to cache ij is going to be math.max of, it's going to be cache I minus, so it's going to be the same thing that we had before, cache I minus 1 j, or cache I minus 1 j minus weights I minus 1. And so what we're doing here is we're saying cache I minus, so we're looking at the previous row because again, we don't want to include the current element. And then we're subtracting, as I said, the weight of the current item from j, because if we include that, then our remaining max weight is going to be the current max weight minus that value. So we have this j minus weights I minus j, which is kind of a mouthful, but it's hopefully makes sense. And then of course, in this case, since we're including the new value again, we need to include vals I minus 1 because we're adding another value. And that's it. That's all there is to this. We just do one of those two things. We fill it in. We go through the entire thing. And then at the end, all we have to do is return cache weights.length. Well, weights.length plus, no, it's weights.length and w. And then we get our result because we're just returning this value here. So let's super quickly go through this as an example. I can fill all these in with zeros again. So we're basically, we're starting by initializing our array, which is going to just be a bunch of zeros. And then we're going to start in the first row, or sorry, the second row. And we're going to, so we're going to start here, or we're going to really start here. And we're going to, and we could probably actually do j equals 1 as well, because we don't need to worry about this case again, because these are all going to be 0 as well. So we're going to start here. We're going to say I equals 1, j equals 1, weights I minus 1. So weight 0 is not less than or equal to w, or sorry, weight is not greater than j. So we're going to come down to, so actually weights in this case is, so if weights I minus 1 is 1, and so it's not greater than j. So we're going to come down here, we're going to say math.max of cache I minus 1, which is going to be 0, j, or cache I minus 1, j minus 1, which is, sorry, I minus 1, which is here, and then j minus 1, because weights I minus 1, so minus 1 is this, and then plus vals, which is going to be this. And so we're going to get 6. And then we're going to continue on. We're going to we're going to go to the next one, and we're just going to continue this. And I'm actually not going to go through this whole thing, but you can see that we're going to go through and fill in these values exactly as we had before. And then eventually we're going to return this value here, which is going to contain our correct answer. So that was a lot. It's a tough problem, as is most dynamic programming. Hopefully that made sense. If you have any questions or there's anything confusing about this, feel free to leave a comment in the video on YouTube or come over to the blog, and there's a lot of content about this there as well that you can learn a bit more there. So otherwise, I will see you guys again soon.